Let's suppose I have a single neuron here, and by definition, a single neuron is a computational unit that simulates the behavior of a biological neuron. So basically, what scientists have done, they have tried to clone the same neuron which we have in our brain and try to put in machine learning and deep learning technologies. So I have deleted all the network architecture here. Here we are trying to understand only one neuron and what goes inside a single neuron. So let's understand what are the basic components of this neuron. So one neuron will have one input. Apart from this input, we will also have weight. So this weight will decide how much influence each input will have on this neuron's output. I will explain this in more detail through an equation, but let's first understand all the components. So after this weight, we have bias. So bias will allow the activation function to be shifted left or right. If you don't know how and what activation function works, don't worry, I'm going to explain you also. But I have created a separate video of how the activation function is used in neural networks. If you want or you are interested in details of activation functions, you can watch through that. Now, based on these three factors, the output will be calculated after applying the activation function on top of it. For example, if input here is, suppose I'm giving an input 10 and weight here is 1, bias also here is 1. So what we will do, we will calculate the x here. So x is nothing but the summation of all the input to it. For here we have only one input, so it would be 10 into, what is the weight here? 1. So this will decide how much influence this input will have on the output of this neuron. That's why it's weight. Then we will apply a bias here, which is 1. So output here is 10 into 1, which is 10 plus 1, which is equal to 11. Now this is our x here. So x here is equal to 11. On this x, we will apply an activation function. So what does this activation function tells? If the x is less than 0 or equal to 0, the output is 0. And if this x is greater than 0, the output is 1. It's very important to understand that if after applying the activation function on this x here, if the output is 0, that means this neuron is not activated. If the output here is 1, that means this neuron is activated. I will repeat this again for you. Suppose this is a single neuron. Let me first delete all of this. Suppose we have a single neuron here, and on this neuron we have this input. So suppose the input we are having 10, and the weight which we have designed or decided is 1 here, and the bias is 1. So we will, to calculate the x here, we will do the summation of all of the inputs here. So we have only one input here. So what we will do, we will do 10 into 1, which is our input into weight. Here is our weight, plus we will do the bias. So bias is 1. So this will give us 11. So x here is equal to 11. Now on top of this x, we will apply the activation function. Now what this, just for the simplicity, I have taken a very simple activation function here. What this activation function does, if this x is less than equal to 0, output is 0. And if this x is greater than 0, in which case it is indeed 11, so our output would be 1. So this neuron, according to this input, is activated. Because the output is 1, that means activated. If the output is 0, that means it's not activated. Now let me give you a scenario in which it is not activated. Suppose input here is minus 10. Weight still here is 1, and bias still here is 1. So to calculate x here, what we will do, the input is 10, we will multiply it through the weight, and then we will sum the bias, which is 1. Okay, let me just delete. I have written the bias there, so it would be 1. So which is minus 10 into 1, which would be minus 10 plus 1, which is equal to minus 9. Perfect. Now x is equal to minus 9. Now on top of this minus 9, we will apply the activation function. So f of x is less than equal to 0, so our output here would be 0. That means this neuron is not activated at all. Very simple to understand. Now similarly, if I have multiple inputs here, for example, I have input 1 here. Let's suppose I have one more input and I have one more input here. So here I'm supplying it 1, here I'm supplying it 2, here I'm supplying it 3. So we have 3 inputs to this neural network, sorry, not neural network, the neuron here, and I have here, let's call this x. So x here would be equal to summation of all the inputs into all the weights. I mean, let's suppose weight here is 2, and let's suppose bias here is again 2, plus we will have the bias added here. So in this case, if at all I have to calculate all the input, this is how I'm going to do it. So input 1 is how much? This, let's start from here, 2. So 2 multiplied by the weight 2. Again I have input 1, so 1 multiplied by the weight, which we have 2 here, 2. Again 3 is the input, so plus 3 multiplied by the weight 2, and at the end we will add the bias, which is 2 here. So how much this is equal to? 2 into 2, which is, it's just a mess right now, so let me write it here. 2 into 2 is 4, 1 into 2 is 2, and here again 3 into 2 is 6, plus the bias here. So this is equal to 4, 10, 12 plus 2, which is equal to 14. So here x is equal to 14. Now on this 14 here, we will apply the equation fx. So f of 14 here will be equal to how much? It will be equal to 1. That means this neuron will be activated. Super easy to understand, isn't it? Let me summarize the 3 scenarios which we looked at. First, we looked at how this neuron will be activated based on the input 10. Weight was 1 and the bias was also 1. In this case, neuron was activated because applying the summation function, which is wi into input of I plus bias. Applying this equation, we calculated the x here, which is equal to 11. So f of 11 equal to 1. In this case, our neuron was activated. Instead of input 10, if I take the input -1, in this case, our f of, -1 into 1, which is -1 plus 1, which is equal to minus of 8. So minus of 8, in this case, output would be 0. So our neuron won't be activated. Apart from this, we also looked at how we can handle multiple inputs. So once we have multiple inputs into a single neuron, of course, we are going to use this equation here. So idea is that we always calculate the x in here using this equation, and on top of this x, we always apply the activation function to get the output. Now this activation function can be of any type. For simplicity, I have just taken here a normal fx is equal to 0 when x is less than 0, and fx is equal to 1 when x is greater than 0. We will have sigmoid, ReLU, tanh, different kinds of activation function. So I have already created a separate video on this. You can watch through that. So this is what happens inside a single neuron.